The very last research at TTIC talk for the year. We have Jungo Kasai. Jungo has been a research faculty here since September, and will tell us about foundation models for speech.
All right. Is microphone on? All right. Okay. Here. All right. So this is going to be a little bit of an unusual talk for some reasons. First of all, I had this title towards speech foundation models. Like 2 weeks ago, OpenAI kind of sold it. That's what I see from OpenAI's demo, if that's right. So I will talk about technical stuff, of course, towards the end. But I also want to share sort of my personal story as an LP researcher. It might help junior researchers or PhD students here, or people who are interested in pursuing a PhD or something like that. All right, so let me start with my personal story. I did my undergrad at Yale. This is, of course, old school. So before starting my college in Yale, I wanted to study philosophy. Like, this guy, Wittgenstein, this guy is very interesting. I wanted to learn about philosophy of language. That was the start of my sort of college career. And then I took some philosophy classes and wrote some essays. Didn't like it much, and I took this course called computational. What was the name? Computational language. Right? It's the old school, so they don't have natural language processing course at the time, but they have this linguistics course called computation and language. And one of the things that the professor Bo Frank was teaching it. He's kind of like a computer scientist by training, and he also knows a lot about linguistics. That's his background. And then in one of his lectures, he says something very cool that was kind of changed my personal career actually. So the thing is, so there's someone who said a word is characterized by the company it keeps. This is kind of like a cliche at this point in NLP because it's everywhere basically. But the idea is distributional semantics. So when you define, in philosophy, how do we define dogs and cats? For some reason we know what dogs are, but we never know their exact definitions, right? And there's this thing called distributional semantics. How do we define these words' meanings? And one approach to do that is computational, sort of statistical approaches to semantics. So the idea is when you define dogs or cats, you can look at where these words appear in your language, right? So dogs and cats probably appear in similar contexts compared to chopsticks, for example. So we sort of know dogs and cats are similar to each other compared to dogs and, for example, chopsticks. Right? So if you use this kind of a statistical approach and use computers to understand meaning of language, you can actually have a very good understanding of language. So that was kind of mind-blowing to me. I mean, maybe for you guys it's just obvious, but I was an undergraduate student and mind-blowing. So that was that led me to pursue NLP research in college, and also and I worked with a bunch of linguists over Rambo in Colombia. So that was my personal story. So today's talk, again, this will be a bit unusual. I will probably first I'll talk about sort of what I've been working on in the past. And then we'll talk about sort of the part two. We'll talk about, of course, LLMs. Of course, we need to talk about LLMs. And then at the end, we'll talk about the future or maybe the present made by, 2 weeks ago it became sort of the present. All right, so when I did my PhD, it was so I did my PhD for 5 years. That was probably the most traumatic 5 years in AI and NLP. People might disagree, but for me, it was really dramatic time. Now, of course, everyone talks about LLM, chatbot, ChatGPT, this kind of stuff. It's everywhere. When I started my PhD, I was interested in more semantics, but then now people talk about this in everyday life. Of course, you can use ChatGPT or whatever for programming, writing, and summarization, etc. Right? So things have changed a lot. So if I summarize my 5 years as a PhD student, of course my PhD, I mean, just like anyone in PhD, it was kind of a mess. I worked on whatever I wanted to do, and then I didn't know what to do in the middle, and then I did random stuff, and then eventually I got PhD So that was great. But if I have to summarize it in a very nice way, nicest possible way, it'll be like this. So in the beginning, again, I was interested in like semantics or syntax, more like old school core natural language processing. That was my sort of pre-PhD or first year PhD. And then after that, I realized, okay, so I've been just working on the English language, right? I mean, core NLP stuff is very cool, but why am I just working on English? I speak other languages. Why not work on multilinguality? So that was sort of the frustration I had when I was a second year PhD or first year PhD student, and I started working on multilinguality. How do we make models work in multilingual settings, not just English? And after that, second year, so while I was working on multilingual stuff, like how do we make models work in different languages than English, I realized that, of course, machine translation is sort of the holy grail at the time. Like, you want to make machine translation work, especially in the context of multilingual modeling, right? So machine translation is sort of one of the most interesting applications at the time for me, and I pursued sort of how do we make these models faster. And in the third year, I also continued to work on machine translation. And of course, towards the end, I worked on like efficiency, how do we make models faster, not just machine translation, but in like generation, how do we make generation faster? Of course, now everyone is interested in generation, but at the time, it was less of the mainstream. But I started working on sort of efficiency and speed up generation, including machine translation and other generation tasks. And then, of course, large language models came at the end of my PhD. So everything has changed. All right. So that's sort of the nicest possible summary of my PhD. One thing I wanted to share, especially for junior researchers, is if you look at this, I thought it was kind of cool. Like the audience of my research got bigger and bigger. The scope got bigger. Of course, the field has changed as well. But as you can see, sort of first I started working on core NLP stuff, and then towards the end, the audience of my papers and research got broader. That is great. Of course, there's nothing wrong about working on niche topics, but that was a nice feeling. I know some niche topics, but also I can work on broader topics, and I feel comfortable with that. That was a very nice feeling I had. So, junior researcher, highly recommended to keep working on different things. And another thing is that if you look at these different topics, they actually correspond to different institutions I was working at. So in the beginning, I was at Yale again, and I did some internship in IBM, and then I went to University of Washington as a PhD student, and I also did some summer internships and stuff. And when I changed my environment, I realized I can do something cool, something new, very comfortably, and I learned from other people, like experts in other subfields, very quickly. So if you have chance, of course, it's great to stay in the same place and work on problems very deeply. But if there's a chance to explore new opportunities, that's highly recommended. This is like the kind of a lesson I got from my PhD. Of course, yeah, most of the things I was wrong, but this might be right. Just like, I couldn't predict GPT will basically dominate the field. I couldn't predict it, but this thing I might be a bit more confident about. All right, so what was happening in my PhD? So the beginning of my PhD was quite interesting. So I did my PhD at University of Washington, I joined University of Washington, and something cool was happening exactly in that institution. So this is called ELMO. You probably don't know what ELMO is. This is like 4 or 5 years ago. But the idea is, of course something right? So the idea is basically we do some sort of transfer learning. So we have a lot of text data in the world, right? On the internet, you can crawl a lot of data from the internet, whatever. And you do an expert prediction or something like that. So if you have a sentence like the first president of the United States is George, and you predict Washington, you keep doing this for basically all the text you have, and then you get this model, basically gigantic neural network, and you use this neural network to do whatever tasks you do. This is quite different from what we've been working on. We had been working at the time because we were training like task-specific models, right? Task-specific model. If you have machine translation, you just train a model on machine translation. You train a model on semantic rule labeling, summarization. But now you have now we call maybe foundation model in the West Coast, but foundation model, and then transfer it to different tasks. Of course, it's obvious now, but at the time it was revolutionary. They got nice paperwork. And then someone, you probably know this name, Sebastian Ruder, he's kind of like an influencer in AI. He said something like, at the time when this Elmo paper came out from University of Washington and Allen Institute for AI in Seattle, he said something like, NLP's ImageNet moment has arrived. So it was kind of a common practice to do ImageNet pre-training at the time. ImageNet is basically, of course, you know, billions of images with classification tasks. And then you train a big model on this ImageNet task and then use it for different downstream tasks in images or vision. So that was kind of a common practice in NLP, like in vision in 2015. And Sebastian said, okay, so now NLP finally caught up with computer vision. Okay, but I thought this was the end of NLP. I mean, no, sorry, not the end of NLP, but the end of sort of a revolution. But I was definitely wrong, right? So like, this is just the beginning of the things that we saw in the next 3-4 years. And at the time, again, I was working on multilinguality. I wanted to make models work in multilingual settings, not just English. So this is a paper, actually, I wrote in 2019. The idea is like, this is, some tasks like core NLP tasks or whatever tasks you like. You train, I was working on something like multilingual Elmo. So this is like, okay, so if you train a Elmo model on a single language like English or whatever, these are different languages, Arabic, Hebrew, Russian, these languages, you can also train a sort of bilingual model, right? You don't need to train a model on a single language. You can train a model on multiple languages. Now it's obvious, but at the time it wasn't too obvious that you can train a decent language model on these multiple languages, and you can use them just like for downstream tasks. And you see, if you compare it to monolingual performance, you see improvements by adding English, or REL here is actually related language. So for example, Spanish, we add Portuguese, you get downstream, this is just the downstream performance, and then you get substantial gains from adding these languages. So here I was doing basically multilingual or bilingual, in particular, bilingual representation learning on Elmo. All right, it works. That's great. But in retrospect, it didn't really take off. Not many people really cared about our paper. Why? So one reason is I didn't use I only use like bilingual settings. See, you can see in the plot, I only use bilingual settings. And then the number of languages is not that many, right? So like I have like 10 or 15 languages. I carefully chose these languages, but that was how it worked. But at the time, there's actually a paper from Facebook, FAIR, cross-lingual language model pre-training. Nowadays, people probably don't remember this, but that became really popular at the time. What they did is basically the same. What we did, except they came later, but then they actually were more influential in some way. They got more downloads, and then a lot of people used their models. And one reason is that they have like 50 languages in the model, right? 50 languages in the model, and they also use transformers. We use LSTM. You guys are like, come on, but yeah, at the time, LSTMs were more like the standard. So these are sort of reasons why the paper didn't take off. But the lesson from that is actually quite interesting. I think engineering is actually very important, even research, especially probably in the field of NLP or maybe computer science. So one reason why I stick to bilingual settings is because it's easier to see the performance gains, right? So if you do this kind of bilingual plots, it's very easy to see, okay, you get some performance gains, you can do scientific studies. That's very nice. That's great, but it's not very useful, right? So like most practitioners and later researchers who want to use multilingual representations, they actually benefit more from 50 languages in a single model, like also bigger model. They might not care what kind of performance gains they get, like in a sort of a quantitative way, but then it's just useful, right? So like people use it. So engineering is very important. And in fact, this paper is actually very poorly written. I will treat you to free lunch if you can explain what they did in the paper correctly. It's very bad. I shouldn't say this anymore. But anyways, so the point is like, I mean, carefully doing scientific research is very important, but at the same time, we should think about how these models can be used. And then I also did only a few tasks, but they also did like question answering and other tasks that were really popular at the time. So lesson learned. And then after that, BERT and GPT-2 era came. So there's one interesting story about BERT and GPT-2. When BERT came out, I couldn't really understand the sort of the impact or importance of the paper. And then actually my PhD advisor, Noah Themis, also agreed. He said we shouldn't give the best paper award to just a straightforward extension of the Elmo we just saw. But of course, he was wrong. BERT got the best paper award in Apple 2019. Another thing that was interesting is Luke Zettelmoyer, who was a PhD, or who was also a professor in University of Washington. We had many hallway conversations, and one of the things he said is actually interesting. So Luke is actually one of the authors of the Elmo paper, and he says something like, "Oh, BERT, this thing is very amazing, but he feels sad that Elmo didn't last for more than a year." So there was an interesting perspective on the same thing. People have different opinions, and even these very well-established researchers sometimes make wrong predictions. And so Luke was kind of right about BERT, I guess. BERT became very popular after, but then he also didn't notice the importance of GPT-2. He said, "Oh, this is a big, gigantic language model. What's this? Like, why are people talking about this?" But then, of course, we know that this was completely a different thing, right? Another interesting thing is actually we saw the moment where you guys all use like Hugging Face, right? So Hugging Face platform for AI, they're like GitHub and AI. It was kind of a BERT actually. I guess BERT kind of helped Hugging Face platform grow very quickly. So one reason is like at the time BERT was developed by the Google team, but nobody really. So Google uses at the time TensorFlow, but nobody really wanted to use TensorFlow. It's kind of a mess. And then of course everyone likes Meta's PyTorch, and then they just rewrote BERT into TensorFlow, or excuse me, PyTorch. And they got really popular because researchers just wanted to use PyTorch version of BERT. So this is an interesting moment. They didn't do much like novelty. It's just an interesting moment when you create something that's usable by many people, you might create something very cool. And now, of course, everyone uses Hugging Face. I use Hugging Face to collect data sets, serve my models and stuff. Maybe I shouldn't talk too much about my research because it wasn't that important in retrospect. No, so I did fast machine translation, like no autoregressive machine translation. How do we make generation faster? I mean, actually, this is actually quite important now because we use generation models everywhere, and then models are getting bigger and bigger. So this kind of generation efficiency is getting probably more important than it used to be. And then I also did a paper showing that my previous work is actually wrong in some way. Like you don't need to do this kind of complicated stuff. You can actually do very simple technique and make it work. So it's okay to do self-criticism. Of course, you can be wrong. Yeah. All right. So that's a lesson. And then GPT-3 came out, and then of course I don't have to explain this, but there's basically a paradigm shift. At the time, we did a lot of task training, but then we started doing a lot of like feature learning. We don't train a model on specific tasks. We just do sort of training on the fly, in context learning, learn from examples on the fly. So that was kind of a moment when a lot of things changed. Okay, so you do like you can use GPT-3 for translation, like English into French into English or something like that. And then at the time, I thought evaluation is very important. How do we actually? We have lots of generation models, but then I thought it's very important to evaluate these models robustly. So I worked on this idea of like bidimensional leaderboards where instead of just evaluating models, we also evaluate evaluation metrics as well. So this work was sort of focused on evaluating generation models. And now I think it's more relevant. Now people use like chatbot arena to evaluate LLMs or chat-based LLMs. And I think evaluation is getting more and more important because we don't know which model is better. All right. And then just this is kind of a interesting example. So I actually drew a comic for my paper and I posted on X Twitter at the time. So I mean, we are PhD students and researchers can do whatever they want to do. So that's something I wanted to say. And then of course, these large language models after GPT-3 and ChatGPT, it became more commercialized. So we have large language models and then a lot of things are happening around generative AI models or generative LLMs. There was still frustration actually at the time. So it's great to have a lot of commercial large language models and kind of like democratized, right? So like a lot of people can use these models. But then there's a scarcity of non-English languages. Again, kind of going back to the older theme I had. But so of course, internet users, only 1/4 is English speakers. The other 3/4 are non-English speakers. But then if you look at NLP papers or benchmarks, it's highly English-centric. So at the time, I felt very sort of frustrated and wanted to do something that mitigates this fundamental problem. And one thing that we realized is that so GPT and LLMs, they all have tokenizers, right? So you can't just input text. You tokenize them. So like you tokenize it typically by word or subwords, and then input them into the transformer model. And one observation we had after a while is this tokenizer is actually very not equal among languages. So for Russian or Japanese, my native language, it actually tokenizes words into more sort of smaller pieces, which means that for these languages, the performance often suffers, right? So because if you separate input into smaller pieces, you have to solve more long dependencies, right? So there are, roughly speaking, the same meaning. You have to, in Japanese, you get 20 tokens. In English, you get 10 tokens. It's easier to memorize and do reasoning over English text, for example. And also, because these are commercialized models, they are typically, the cost is calculated based on the tokens they generate or they input, right? Because the number of tokens is basically the number of timestamps you input into transformers. So it's a reasonable estimate for the cost, but it also means that Japanese speakers, for example, have to spend twice as more cost to do the same thing. So that was really frustrating. We've had this observation and then suggested a way to mitigate this by changing the tokenizer. And actually they did. OpenAI actually had a office opening in Tokyo, and they actually had this tokenizer change. So they actually show that twice as faster GPT-4 performance on Japanese because they changed. I think they didn't disclose everything, of course, but people think this is because of tokenizers. And then they made headlines. So if you're OpenAI, you just need to change tokenizers, and then you get a headline, and then people are really excited about you. So that's kind of cheating. But yeah, that's life. All right. All right. So let's summarize what I learned. One thing I learned is that I was most of the time I'm wrong. So I shouldn't just trust my intuitions. So first of all, I didn't expect that scale up these models will change the performance so substantially. Performance and usage potential of these models. And another thing is that, again, sometimes scientific research is important, but making something usable by many people is also very important. And if you think about it, it's actually kind of obvious. So So for example, transformers became very, very popular. Maybe not because these models are really good. These models maybe because these models became popular because something like hardware determinism. It worked very well on current hardware. We have like GPUs and TPUs. It's easier to parallelize transformers. So if however many times you read a transformer paper in 2017, you can't really realize, you can't really predict that transformer will be as successful as it is actually now. Because there's many co-founding factors. Like we have hardware that enables scaling up of transformers very well. Right? And so that's kind of like not really scientific. You can't just read papers and compare benchmarks and understand the superior, like the performance of transformers. You need to think about what we have as tools in society and in the field. And if you think about the name computer science, actually, maybe computer science is called computer science because it's not science. Just like OpenAI is called OpenAI, of course it's not open. And another thing is like Safeway. Safeway is maybe called Safeway because it's not safe. So maybe there's something profound there. And then we shouldn't overly trust experts. We sometimes can't predict the future. Like just like I couldn't predict myself the potential of GPT. And also, I was really surprised that the moment that transformer or GPT became so popular and so useful was chats. Like I don't want to chat with people, let alone talking to machines. But for some reason, people like that. So that's an interesting find. So I really don't know anything, but again, you know, we should keep going. So I wanted to do something that can probably make some difference. So I wanted to introduce this project called Japanese GPT Fugaku, or now it's called Fugaku LLM. It started like a year ago, but now it's closing up. It's kind of a year-long effort. There's a lot of people involved. So let me give you some context. So in 2019 to 2022, of course, there's many large language models developed by many people. Like English is, of course, OpenAI. There's also other players. There's also Chinese LLMs. And there's also multilingual. I was also involved in this project, Bloom. This project actually involved many European languages. They had French. They didn't have German. Apparently, French people didn't want to include German in their training because Hugging Face was leading this project called Big Science, and Hugging Face is actually a French company. And then I was talking to Hugging Face people at the time, and they had a very interesting argument. So they ended up getting supercomputer resource from the French government, and they had this grand proposal. They said something like, the two AI superpowers, US and China, are threatening the AI ecosystem of France. So that was an interesting moment when sort of these models are getting more and more sort of national concerns, not just research models. So when I heard that, I thought, why we can't do this for Japanese? I mean, it's a fairly big language, and there's many researchers in Japan, of course. And more importantly, globally, Japan has one of the fastest supercomputers in the world. It's one of the biggest countries that have that have very strong supercomputers. And that one of them is actually Fugaku. Fugaku is CPU-based supercomputers. Did anyone here train? Has anyone here trained like machine learning model just on CPUs? Probably not. Oh, sure.
Well, you know, before
yeah.
10 years ago, that's all we did.
Yes, that's right. I forgot. But did you guys use like 100,000 CPUs? We use 100,000 GPUs here. CPUs. Yeah, so it's a crazy project. Who wants to use like 100,000 CPUs? So the project was like, you have to rewrite PyTorch and the distributed training library to make it work in CPUs and make sure that there's no bottleneck and it's kind of there's a lot of things going on. But in principle, it was 10 times faster than the French government supercomputer they used for Big Science. So it should have been okay. It should have been doable. However, there's some problems, of course. So CPUs are not really, these supercomputer CPUs are not really optimized for matrix multiplications. Matrix multiplications, of course, are fundamental parts of training transformers, right? So you do a lot of matrix multiplication, like 64 times 64, 64 by 64 matrix multiplication or something like that. But it wasn't really optimized for that. So we have to sort of do heavy engineering that probably some people in NVIDIA have been doing on, right? So it turns out one single CPU we had was 50 times slower than A100 GPU. So that was sort of the state of the art at the time. Now it's H100. I think H100 is roughly speaking 3 times faster than H100, A100. So 150 times slower. So that was crazy. But we have many CPUs. We have many CPUs, 150K CPUs. So let's do it. But then there's also communication cost. We have to make sure that the communication is smooth. Otherwise, it becomes a bottleneck. And then turns out empirical and theoretical performance difference for CPU is bigger. For GPU, it's about 40%. You know, it's because of like all these NVIDIA efforts and these software stack. But for CPU, we only have 10%. Now, I think towards the end of our project, I mean, this project just finished, but we got to like 30% CPUs. So that was great. It worked out. And then this project involved many people, many Japanese universities and Japanese companies. Fujitsu, also Fujitsu is the manufacturer of the CPUs of Gaku, big company. So this took off. All right, so that just finished. So that was about sort of the present. I want to talk about the future at the end. So we've been talking about LLMs, like text LLMs. Mostly these models are just text LLMs. But then a lot of people agree that models should become more multimodal. So one thing is like speech. Can we make models in a way that can process speech or audio input in an end-to-end way, just like we do text LLMs in an end-to-end way. So that was so there is actually, I mean, I'm wrong many times, but there's a decent sort of educated guess. We think speech models will become more end-to-end. So this is the 2023. This is state-of-the-art speech-to-speech sort of speech-to-speech translation or speech-to-speech models for Meta in 2023. It's called Seamless M4T, and you can see these boxes are basically separately, pretty much separately trained models, like modules, and they are combined, right? So you can see this is very complicated. This is very different from GPTs or LLMs. But actually, this reminds us of the NLP pipeline we had before these generative models came in. So we had again, core NLP models like syntactic parsing, semantic labeling, POS tagging, and then we combine these modules. These modules are separately trained, and these modules are finally used to, in a pipeline way, choose to predict the last, sort of generate text or do some classification, whatever. Right? But if we have a diagram for GPT in the same way, it'll be just a big transformer and end-to-end. Right? So just do LLM training. So our guess is that this will change. Speech will be more end-to-end as well. And that's sort of the educated guess as a researcher. But there's, of course, reasons why we want end-to-end speech models. Right? If you don't have end-to-end speech model, if you do like speech-to-text, text-to-speech, or text-to-text and text-to-speech, something like that, pipeline, of course, we'll have lack of generalizability. Just like machine translation models before wasn't really generalizable. Right? So like if you train a task-specific model in speech, it will be less generalizable. And then we can't use in the same way as like LLMs. Like we can use LLMs for whatever, for email writing, coding, whatever. But we want to do this for speech as well, eventually. If you want to pursue generalizability and also customizability, you want to customize these models to your tasks. You can't do this with a specific model, right? So you need to have a sort of foundation model and then customize it to whatever task you're interested in. So I think that this is sort of the direction we should go. Of course, there's also information loss. Right? So like speech has, of course, rich information, like emotions, tones, and pitches and voice. if you use pipelines, you lose this kind of information, and it gets very hard to use speech models in interesting ways, right? So for example, if you want to do like, let's say we automatically dub Friends episodes into Japanese. Like if you use pipeline approach, we're kind of doomed. We have to preserve the pitches, voice possibly, and also background noise. We need speech-to-speech model to achieve this kind of goal. And lastly, there's latency problem. If you do pipelines, typically it takes more latency. Human conversations typically have less than 0.25 second of gaps. But then if you do pipeline, usually it takes longer. Although you can also try to make it faster, but it's not ideal. So if we want to have natural conversations with these models, we need to have speech-to-speech model. So like this will be speech-to-speech model. So what are we missing in speech-to-speech model? So interesting approach is, so the technically very interesting thing is like tokenization. So we tokenize text, so we can actually tokenize speech or audio input in the same way. So this is called encodec. This paper was written, I guess, published in 2022. So let me just do whiteboard exercise how it works. So let's say we have 2 seconds of audio. Is just the audio wave. 2 seconds. And then let's say our sample rate is 16K hertz. So typically we have 32K, right? So 16K hertz, right? So like these are floating point numbers, right? 0.1, 0.2 or something like that. So this is the representation of the wave. But nobody really wants to work with this, right? So this is too long for 2 seconds. So the way it works in tokenizers is we sort of do convolution neural net downsampling. Details are not very important, but let's say we downsample it to t by something like d. So t is typical, well, let's say it's kind of like 128, much smaller than 32K. D is conventionally it's like 1024. So this is the downsample. But of course, you have to downsample in a way this kind of preserves the information here. So we have the upsampling convolution neural network. Sometimes I think that vision literature, this is called hourglass. So hourglass structure. And then at the end, you have the reconstructed 32K the wave. Right? And the objective is you train this model to minimize the difference. There's more details, of course, but basically you minimize the difference between these two. It's kind of like autoencoding. But then this is actually, because this is the output of convolution neural net, this is still floating point numbers, right? So like 0.1, 0.2, blah, blah, blah. So we want to discretize it because we want to make it just like text. So the way it works is what they called RVQ, residual vector quantization. So residual, so what's the why it's called residual? But basically the idea is you have many code books, what they call code books. So let's say D by, so number of codes we have. So like, let's say N, Q, this is the number of codes. And we have many of these. So these are floating point numbers. So these are vectors. And then every step, let's say we take this one time step, d-dimensional vector, we compare this vector to these different codes, and then you choose the most similar one. And then after that, you take the difference between these two, and then we keep doing this for many code books. And at the end, this can be discretized, right? So these are codes. So let's say this is index I, and you choose index j, so you get I, j, blah, blah, blah. So this is a token sequence. So interestingly, so if you can do this kind of tokenization, you can solve speech-to-speech foundation model in a similar way. Like you can do left-to-right training using this kind of approach. And then this is, of course, done by many people. One of the interesting papers actually came from OpenAI Jukebox. They did similar, something like this. And you probably realize if you do this kind of training, this kind of autoencoding training, there's going to be like rich gets richer effects. Like nothing really prevents us from choosing one code all the time, right? So like a few number of codes become very significant, and they are only used during training. So there's of course training tricks that make it work. So details in the paper, but this is kind of an interesting way of doing tokenization. And one thing that's cool about OpenAI is actually they have a very simple solution to do this. If I work on this problem as a researcher, I would probably try to use like EM algorithm and complicated stuff. But it turns out very simple approach works. So like you just keep track of a sequence of codes that you end up choosing, and then during training, if your codes become too homogeneous, you just randomize some of them. You just randomize the ones that are not chosen. Randomize in a way that are close to the training samples you have, so that these codes will not be ignored, right? So you can force it to use these codes. So that idea was actually that idea came up in the Jungo Kasai paper in 2020. Anyway, so that was cool. Right. Okay, so that was a little bit of technical stuff, and then we can use this tokenization model to do left to right training, and it kind of works. Lastly, of course, we want to talk about GPT-4o. I think they did probably end-to-end speech model training. We can tell from their demo examples. It's clear that they didn't do pipeline.
Today,
one thing that was cool, and I wanted to think about.
Sounds like we're in for an intriguing interaction.
So they're talking.
Are we talking
Scarlett Johansson.
unique fixtures or colors that add to the outfit?
There's a noticeable bright light overhead.
So they did something.
Casting a focused beam downwards, which creates a spotlight effect. This adds a dramatic and modern feel to the scene. The rest of the room is lit more softly, possibly by natural light filtering.
Did anything unusual happen recently?
Interruption is happening.
Yes, actually.
Yeah, and then you can actually, it works, right? So like you can interrupt, and I wonder, so like I was wondering like how they did this. One possibility is like actually they have multiple, so usually when you do left to right training or regressive training, you only have your own input, right? So you predict next word, or next token. But then you need to know what you get from the outside world to do this kind of interruption. And I can't really understand how they did it, but I can probably have some guess that they did. But anyway, so this is it's clear that speech foundation models are really cool if it works. All right, so this is sort of the end of my talk. It was a bit unusual, as I said, but yeah. All right, so that's it. Yeah, thank you so much. Yeah.
What is the so I believe that GPT-4o they train end to end as a multimodal model, right? So, in your opinion, what is the merit of training speech and text together?
Oh, that's a really good question. So, I'm actually trying to. I really want to do research on this. I think one possibility is like text guidance actually helps a lot. So if you think about translation, so you can do purely speech translation, right? So like you speak in English and then do Japanese. But then it turns out if you just train this model, there's no enough signal. Like you have to have sometimes text speech, speech text, and then speech speech. So maybe having multiple modalities actually help, especially like text is less sparse, right, than text speech. So it's kind of easier to learn from text. So I think there's benefits, but I'm not sure that would apply to like bigger data or super large models.
So basically, text training gives the model a good prior knowledge.
Yeah. I mean, it's kind of translation is one example, but if you think about it, it's kind of obvious, right? So because it's just like you can't learn everything from speech. So like, text is like a lot of knowledge. Yeah, it's interesting, very interesting.
Thanks for great talk. I'm thinking so when people are currently talking about multimodal language model, like we have different kind of like technical routes, like as you explained in today's talk. One route is like we convert different forms of modality to a sequence, like image to a sequence of patches, like audio to a sequence of some in feature, and then we somewhat fusion those inputs together and to make our multimodal model. That is doable, and there are also some other approach, like maybe we can, like people say we can edit it or inject some like a diffusion model or some other adapter from vision and then combine them together, like maybe in some intermediate layer. So how do you view this kind of like a technical rules, and what's your vision about whether we should like whether the future multimodality model would be putting everything, convert everything into sequence model, or like just other approach? Yeah.
If I have to bet like my money, I probably choose sequence models because it's probably just simpler and it's just easier to scale up. But it's also frustrating. Like why do you have to like these models are like continuous, internal vectors are all continuous values, but you have to tokenize it first and then make it. It's kind of a bit frustrating. But I think at the same time there's also hybrid. Actually, I didn't say that here, but actually there's like a so for detokenizer. So you tokenize these words or the sequence, audio sequence by doing or audio into tokens and then detokenize it at the end, right? So actually there's a diffusion model to do this. So you are doing this tokenization in the pre-training part, but then when you do detokenization or make it audio, there's actually audio or diffusion model that actually outperforms this convolution neural network approach. So I think that we'll probably see some hybrid, right? So like it's not like we're not going to use diffusion models. Probably useful, especially your tokens are probably limited. If your tokens are not very accurate or you don't have too many tokens for audio for some reason, like for latency problems, you have to reduce the number of tokens you generate. I think that would be probably, so these diffusion models will be useful anyways. But then I'm not sure these models, these models will be completely integrated into the big model, like foundation model. I'm not sure. Yeah, so I would probably bet on sequence models. Yeah.
Because I asked the last question because if we take a look at like previous multimodal papers, many people are talking about like kind of like feature fusion method, like we can have the different model encoding a different modality, and only as like maybe last layer or some intermediate layer. That is somewhat like a mainstream method, like in many papers. So I'm wondering.
Well, it's changing. DALL-E 3 was trained. I feel like I'm a salesperson of OpenAI, actually. Anyways, they do this tokenization. So there's kind of two camps of methods, and then they kind of constantly compete with each other. I think they'll probably converge on something similar anyways, right? It's an interesting issue.
Any last question? Yeah.
So when you tokenize, say, speech into, say, course token or final token like RBQ1, then for course token, you inevitably lose some information, but for RBQ kind of token, you kind of have a really fine token that's too long for any model.
Yeah.
So I'm just wondering what's your opinion on that.
Yeah, I see. So yeah, by definition, by design, these codebooks get less and less important as you go to the later codebooks, right? But when you do this left to right training, you kind of equally use these tokens, right? So I think sometimes it becomes a problem. Like if you sometimes like you have 32 codebooks and you train on these 32 tokens, 32 by timestamps, right? But then the last 20 is probably not as important as the first 2, 3. So that is one problem. I think there's multiple ways to mitigate this, like just focus on, like do some sort of weighted training, like you have more weight on the first tokens or first codebooks, or you can even ignore, it's great to have this kind of option to have like more fine-grained tokens, but you can ignore these tokens. You can just choose the first 3 tokens and it works okay. We're not going to be able to like produce very high quality music if you just don't do like 32 tokens. But then 3-4 tokens for human speech is fine or something like that. So I guess it depends on the application, and having these codebooks and having possibility of making it more fine-grained is actually a great thing.
I'm also thinking about like the resolution. If you have like a lower resolution, you can possibly model long content.
Yeah. That's true. So like longer. Yeah. That's possible if you use like fewer tokens. Yeah.
Okay, let's thank Jungo again.
Yeah.